this is problem 29.27, and it says, consider the hemispherical closed surface in this figure. The hemisphere is in a uniform magnetic field that makes an angle theta here with the vertical, like this. Calculate the magnetic flux through A, the flat surface S1, and the hemispherical surface S2. So to do that, well, we know that this is a flat surface that we can draw like this, and it has an area vector pointing like this. The equation for the magnetic flux is just the general equation for flux. It's going to be B dot A, where this is B and this is A here. But it's important that B is coming in like this, right? So what we're going to do is say, well, B dot A is B times A times cosine of the angle between them. So the area here, it's the area of S1, pi r squared, and then B is just B. And then we're going to have the angle between them, and it's going to be cos of 100 minus theta. The reason why we do that, again, is because this is pointing in this direction. So it's kind of like the opposite. So essentially just gives us a negative sign here. So we get negative b pi r squared times cosine of theta is the flux through the flat surface S1. Now we know that the total flux here, because we're dealing with magnetism, is equal to 0. So that means that the flux here, so the amount of magnetic field coming inside here, has to also be exiting here as well. So it's going in, coming out. So we say that phi, the flux through S2, is equal to negative the flux through S1. So all we do is we take this number and then we times -1. So then the flux going through S2, it's the same amount, but positive b pi r squared cos theta. Hopefully you remember from 2 videos ago, like the theory one, the reason why this is true, this is Gauss's law in magnetism, is because in magnetism, we don't have monopoles, right? We only have dipoles. So then anything going out always comes back in. So it's like either going, it's essentially like it's going through it, but there's nothing like just purely coming out of an object like this. Like that doesn't happen in magnetism like it does with electricity.